Ok, so, ça marche le son? Oui. So, we can finish the proof of this proposition. So recall that this proposition, we started from a pointed braided monoidal category. So where is it? Yeah, so this is what we did yesterday. Premetric group and pointed braided fusion category. And so the proposition we will finish to prove quickly today is that we start from a pointed braided fusion category and we make a premetric group. This provide, in fact, we will see this provide a functor from the category of this object to the category of this object with appropriate morphism. And so we need to prove that what we get here. So we made a specific function, and we want to prove it is a quadratic form for the group G associated to the pointed fusion category. So it reminded just to prove that this function is a bi-character. And in fact, we finished yesterday by this diagram. So in fact, we made such a diagram here with two string and two string. We get this decomposition using hexagon axiom, and we can make the same kind of decomposition with 3 string on the left, 3 string on the right. So we get something a bit more complicated, but it's okay. So now it remains to consider this as a scalar. So this braiding as a scalar. So we know we are in a pointed case. So this tensor product is a simple object. This is simple object. Okay. So we have one scalar for that, and we will consider the scalar for every braiding here. We will get an equality between two scalars, and by rearrangement, we will get the expected B character, proof of B character. So, as a scalar, you have C X tensor Y tensor Z. So this braiding X tensor Y tensor Z equal to so you have, so I will write product. So you have this one, so C braiding C X Z times this to one corresponding to braiding C Y X times braiding C Z Y. So Y X Z Y, okay. Times. So I write a product in 2 dimensions like that, just to better understand where it comes from. But you can write the product in a single line. It's okay. So product CXX times CYY times CZZ. So it's okay. XX, YY, Z times CXY times CYZ, and finally CYZ. xz. Then we will group together some components. So we will group this one with this one. This one with yx, xy. And this one with this one. So you get. So remember that x, y, z correspond to G1, G2, H. So by the previous definition, this is a scalar Q QG1, QG2, QH. This and this correspond to B G1H, etc., etc. So this is equal to, and this correspond to Q G1 G2H. So in other words, Q G1 G2H equal. So B G1H times B G2H times B G1 G2 times, so this corresponds to the three color, times QG1 QG2 QH. Okay. So we have this one and this one. G1H. And the green. Now, but by definition, B G1 G2 equal Q G1 G2 over Q G1 Q G2. So we get, so we can group together, so we can multiply. So this is just this. So Q G1 G2H equal BG1H BG2H Q G1 G2 QG1 no QH. Okay, and finally so now for conclusion, so if you put so wait, what about now? So B, so this one BG1 H times BG2 H equal Q G1 G2 H over Q G1 G2 QH, which is equal to, by definition, B G1, G2, H. So this is what we wanted to prove. We got this equality. So we proved that this B is so it's a B character. So we just need to prove it for the left variable. The right variable is come from the symmetry. So that's okay. Good. So in fact, so this so the rest of this section is dedicated to prove in details the following theorem. Is dedicated to prove the following theorem. But we skip the proof. Theorem. So this is a correspondence between parametric group and pointed braided fusion category. The theorem, the functor induced by the previous proposition, is an equivalence of category. Equivalence of category. Between so as follow. The category of pointed braided fusion category as object and braided tensor functor as morphism. Category of pointed braided fusion category as object braided tensor functor as morphism and the category of parametric group as object and orthogonal homomorphism. Orthogonal homomorphism as morphism. Okay. Okay. Good. So we get the expected complete characterization of the pointed braided fusion category in terms of in the group framework. Okay. So I will finish this section with by providing the list of equations that such pointed braided fusion category should satisfy. Equation about the 3 cocycle omega and the given by the associativity constraint and the commutativity constraint. So you can reduce everything in terms of equation. So I will quickly write that as an exercise. And then we will start the section about the center, the Drinfeld center as a braided category. So the next session will be mainly dedicated to prove that the Drinfeld center is braided. So before that, so let C be skeleton of the pointed braided fusion categories. Vec G omega C. So you have the associativity constraint. The associativity constraint is given by that, and the commutativity constraint will be given by that. So the associativity constraint is given by a function omega from G cross G cross G to the non-zero scalar. The commutativity constraint is given by a function C from G cross G to the non-zero scalar. So here we identify the braiding with this function. This is a braiding in the category. This is a function on group theory, but in fact, we identify these two. So the pentagon axiom and the hexagon axiom can be reformulated into the following equation. So because it's written as an exercise, I should say show that the following equation. So the first equation will be the reformulation of the pentagon axiom. So we will make omega, this map omega, a cocycle. So we already did this exercise in details for the pentagon axiom. And for the second type of equation, I leave it as an exercise. So for all G1, G2, G3, G4 in the group. For the pentagon axiom. Already proved, already mentioned. I can say already done. Already done. Already done. So remember, you have something like that. I will try to write correctly. G1, G2, G3, G4 times omega. G1, G2, G3, G4 equal omega G1, G2, G3 times omega. Oh, there is no G4 here. Okay. Times omega G1, G2, G3, G4 omega G2, G3, G4. So cocycle. Omega is a cocycle. Okay. And the hexagon axiom. Hexagon. So this is mainly, this part is mainly the exercise. So you combine omega and C, but it's just a reformulation of the hexagon diagram in this case. So omega G2, G3, G1, C, G1, G2, G3, omega G1, G2, G3 equal C of G1, G3, omega G2, G1, G3, C, G1, G2. And the second one, G3, G1, G2 inverse, C, G1, G2, G3, omega G1, G2, G3 inverse equals C, G1, G3, omega G1, G3, G2 inverse C, G2, G3. Making a so-called abelian cocycle. So the first line, make omega a cocycle, and if you have everything, this is the equation for abelian cocycle. Okay. So it's an exercise, just reformulate the hexagon diagram in this case. Okay. So we can go to the next section. Center as a braided category. Center as a braided category. So you will see I added a lot of details, a lot of picture in this section, just to understand just to digest the mechanism of braiding and center to digest all that. But most of the time it's considered as straightforward in the book. So, okay. So, okay, so maybe we can put that here. So let me briefly recall how we define the center. Recall the object, the tensor structure, and the morphism. Yeah. Object, morphism, tensor structure. So recall that. So the object call that. So the center is C of a monoidal category. C as for object pairs Z gamma. So we define Z gamma, but here I want to add the small z here. So remember that not all objects of C appear as an object here. And this one is not unique for, I wrote it like that, but you can have several natural isomorphism here. The point is here, we will manipulate a lot of such couple with X, Y, Z. And if we don't put these indices, we will be lost. So, warning. There may exist several different natural isomorphism for a given Z. So this gamma is not a function with Z mapped to a natural isomorphism. This is just a notation. It is just a notation. Okay, so notation. Just notation. Okay, so now so here Z is an object and gamma like that, Z is a natural isomorphism given by the collection. So, equal is a natural isomorphism from X tensor Z to Z tensor X satisfying the second. Remember that we realize that it satisfies the second hexagon axiom. The second hexagon. Make it. That's why we call it a half braiding. And we have the picture. So the picture. Can I change the color? I wonder whether I can change the color. Oh, yes, cool. Good. For the picture, remember, XZ, and this is gamma, like that. Okay. Okay. The picture for the half braiding here. The picture for the second hexagon. Picture for the second hexagon. So you have X, Y, Z. So like associativity constraint, then the braiding. And then again, the associativity constraint. Okay. Here it is gamma. X tensor Y, Z. And so by definition of the center, that satisfies this second hexagon picture. So X, Y, Z. So we just first make braiding here. Associativity, identity, braiding. And that's here it is. No, this color is not visible. Like that. Okay. So here it is gamma X Z. Here it is gamma Y Z. Okay, so that is known. So we have a half braiding. So what about the other hexagon? In fact, the other hexagon will be given by the tensor structure. So we know that the tensor structure is as follows. the tensor structure on the center is as follow. Wait, so let me, maybe if I have, can just write everything in this picture. This, so x z gamma, so gamma z, tensor z prime, gamma z prime equal prime gamma z prime. And gamma z prime is defined by the following picture. Picture for gamma. This picture, this is not a commuting diagram, this is just the definition. It's not a property, but it is the definition of gamma z prime. So you have so you write gamma z prime like that. So x z prime. And you make the braiding. So here is gamma z prime. On x, and that's equal to equal like that. So how to write that? So you have, I don't have so much. Yeah, I can just push that a bit more on the. A lot of room here. Should be enough. Okay. This is equal to the following. So you have x z prime. Associativity, and then braiding, associativity, braiding, and again associativity. Okay. So here it's gamma xz. Here it is gamma xz prime. Okay. So okay. So this tensor product defined like that. So this is a definition. So it's the tensor product for the object of C and for the natural isomorphism is defined like that. This natural isomorphism is defined like that. So this provide, we mention a structure of monoidal category. Monoidal, and we checked that before. Checked before. When I say before, it's not in this page, but it is in some previous session. Okay. So, picture. Okay, so now so now what about the morphism? Recall about the morphism. In fact, we will need all this recall to prove that this Greenfeld center is braided. So that's why I take so much time to make all this picture. So recall that, in fact, the Hom set of the center is a embed or is a subset of Hom set in C. So the morphism between these two objects of the center are given by morphism between Z and Z prime. So it's an embedding. So I guess you can make this. So it's an embedding. Maybe it will make sense to call that a natural embedding. So as follow. Oh, so it's time for the pause. So I will finish after the pause. So I will draw the picture for the morphism after the pause. Okay, so we can restart. So during the pause, I try to make this picture a bit more readable. The border, I put them in some black box like that. It's better than before, but anyway. So what about, so the morphism of the center are given by definition morphism here satisfying some property from morphism here satisfying some property So so the morphism commuting with the braiding in some sense. F z to z prime such that you have the following picture. So you have. So if I continue to write picture in green, so x, z, z prime. We have the braiding equal to x, z. Z prime. Okay. So this is, so the morphism in the center are morphism here, such that commuting with the braiding. So gamma x z prime here, gamma x z. And so in the rest of so what color? This one. So be careful. Not this color. So the morphism here will be identified. So the morphism here will be identified with their image via this embedding. So we will talk about morphism here. We just not as a morphism here. We identify with embedding. Will be identified with their image via the embedding. Will be identified with their image via the embedding. Okay. So now we can state and prove the fact that the Drinfeld center is braided. Proposition. So the Drinfeld center has braiding given by the C z gamma z z prime gamma z prime. My definition is just gamma z z prime. So the braiding is given by this collection of isomorphism. So this is an isomorphism in the center. This is an isomorphism in C, but in fact, we will prove now that this morphism satisfies commute with braiding. So this is also a morphism in the center. So via this use because we identify that with the embedding, we just write this morphism like that. So here is, so from Z gamma Z tensor Z prime gamma Z prime to prime gamma Z prime Z gamma Z. So this is equal to Z gamma Z tensor Z prime Z prime Z gamma Z prime Z. Okay. So as I said, we first need to prove that gamma Z Z prime is a morphism in the center. So as I said, so there are several points to check. There are several points to check to do this proof. All these checking are straightforward, but we will do it in details to better digest the mechanism here. Otherwise, it's a good exercise to do, but in the book, it's written as straightforward. It's just a straightforward checking. But I wanted to do it in details, by picture at least, to understand, in fact, what happened, because, in fact, the notion of Drinfeld center and braiding and is one of the most important objects in this course. The fact that the Drinfeld center is braided, and in fact, we will see later that it is modular. This is one of the most important results. That's why I wanted to understand the mechanism in more details. So first, as I said, we first need to check that gamma Z Z prime is really a morphism in the center. We need to check that gamma Z Z prime is really a morphism in the center. So this checking reduce to the following picture. So now I need more space. So, okay. Okay, so we want the braiding to commute with some other braiding. So we start from X Z Z prime. So this is Z the tensor Z prime we have here. So the braiding. This is a morphism F. Gamma Z prime Z. So this is the box. Let's call it. So we will remove that. So this is the morphism F as here. We want it to commute with the braiding. So we have that. The braiding. Okay. So this is here it's gamma x z tensor z prime. But so the first step is to develop this braiding. So this braiding is the braiding for the tensor product. So it's given by definition as follow. So equal by definition of that. So here we will develop this part. So wait, so how should I write that? Let me take this green. Gamma Z prime Z X. Okay, so you just rewrite this picture, but you change this one by its definition. So you have X Z prime. So we rewrite that. And then, so definition of the tensor product at the braiding level. So remember, you first apply associativity constraint, braiding, associativity constraint, braiding, okay. So this is this box. Here. Okay. And I forgot something. No, it's not complete. Wait. Forgot an associativity constraint. Okay, so we have also to come back here. Wow, wow, wow. Okay. So this is really this box. Okay. Now, now maybe you recognize here that you can apply the Young-Baxter equation, Young-Baxter relation here in the non-strict case. So we wrote the picture for the Young-Baxter equation, Young-Baxter relation here. There is a Young-Baxter relation without assuming to be strict. So this is what we will do now. So equal by Young-Baxter. Young-Baxter. Two. So, x z prime. So you move. So you do that, and then that. And finally, this one. Okay, so this is Young-Baxter. Okay. And finally, we apply again the definition of the tensor product. So we can apply the definition of the tensor product here. No. To go there. So equal by definition again. Or maybe I can just write this like that. X, Z prime. Okay, so we have that, and we can write. So you apply, you come back, and we will be done because you see the function across the braiding. So it is equal to x z prime Okay. Okay. So that's okay. So this picture proves that gamma z prime is a morphism in the center because should change the color. Sorry. So what color? Black. Oh, it's not nice. Okay. So that's okay. Okay. Now we need to check the two hexagon. So this was here. Now it is here. This is what we wanted to prove. Now it remains to prove. It remains to prove, to check the hexagon axiom. So okay, so now the hexagon axiom, the objects are in the center, so you have one object x gamma x y gamma y z gamma z. So you associativity constraint, and then braiding. I don't have enough place. Braiding. Okay. So we want to prove that this, this decomposes in the center. So here it is gamma x tensor y, x tensor y, z, like, so this is a braiding between, so you have x tensor y, x tensor y, gamma not Z, sorry. So I will change the color. X, tensor Y. Okay. So you have this braiding, but we know by definition this is equal by definition of equal to that. This is a definition. And so we know that this we know that but gamma Z is a half braiding. So we can apply, so we get the second picture, the second hexagon for free, because this is a half braiding. So by the definition of the center, this already satisfies the second hexagon picture. So this is equal to gamma Z is half braiding by definition also. Definition of the center. So the second hexagon is given for free. So X, gamma X, Y, gamma Y, Z, gamma Z. So braiding associativity constraint, braiding, and I forgot something. So wait. Yeah. So we should have so remind us to check the hexagon. So wait a minute. Wait just a second. Let's check something. Yeah, okay. So here I should also come back. Like so it's okay. So it's okay. This is the second braiding, which is given for free by the definition of Drinfeld center. So here we have, so it's gamma YZ equal gamma Y gamma Y C gamma C. Gamma XC equal gamma X. Okay. So it's okay. So this is Okay. Now, okay for this hexagon. Okay for this hexagon. Now, what about the second, the other one? Now, the other hexagon. So X, and the other hexagon will be true. We will need, yeah, it's straightforward. So Z. So we have that. So first you have the associativity constraint, and then the braiding. Okay. So here you have y tensor Z gamma y tensor Z object. Here it's y Z gamma x gamma x, not y, gamma x y tensor Z gamma y tensor Z. And we know by definition, so we apply the same thing, gamma x y tensor Z. We know that this is that by definition, so we can develop this grading as before. So it's equal to by definition of gamma x y tensor Z. So the same thing that we will replace that. So we already did that two times. So x gamma x y gamma y Z gamma Z. So you have that, and that. And then we have the associativity constraint. Okay. And then we have the box. So this box should be, so the development of that is you apply the associativity constraint back, and the braiding, associativity constraint, braiding, and associativity constraint. So this is my box. Here. Okay, but so we need to finish. So what did I miss? So again, I missed something. Okay. So I missed the last associativity constraint here. To match with the definition. Okay. So, okay. And so we have to do the last associativity constraint also. But you see that we apply an associativity constraint and its inverse, associativity constraint inverse. So you can just draw line like that directly. So it's equal to by vanishing of successive associativity constraint like that. So we can get something simpler. So x, y, gamma, y, gamma, z. So we get exactly so braiding associativity constraint, braiding, and that's all. Which is here gamma x, y equal, etc. Gamma x, z equal, etc. So we really, so here we applied, we proved this other hexagon by by using the definition of the tensor product. Yeah. And for the first was thanks to the half braiding. So it's okay. Okay for this other hexagon. And so this is the end of the proof of this proposition. Okay. So it was quite pictorial. But you see, it's very canonical in the so general framework of monoidal category. We are able to prove that the Drinfeld center has a braiding. So this is really, really canonical. In fact, the Drinfeld center was more or less created to match, to get a braiding like that. Okay. So let me finish by writing some exercise. So recall that we prove the Drinfeld center of the opposite of a monoidal cat. So C here should be tensor or monoidal. Is tensor equivalent to the Drinfeld center of C? So the exercise is to show that so it's no more braided equivalent, but it is if we had the reverse braiding. Reverse braiding. So opposite go out by reverse. And as braided equivalence. So recall. Let DC be a braided monoidal category. D rev C. So the braiding of D rev is C prime, such that you have C. So you have C. How to say that? D rev equal D C prime with, so if C prime xy equal like that, xy C. So it just, you see, the reverse, you have the branch. This is a X string which is above here for the reverse, whereas we usually put the X string. So in this here it's on the bottom, here it's on the top. Okay. So this is definition of the picture for reverse. I forgot to write that last time. So this was the exercise. And that's all for today. Tu peux arrêter.